All right. Hey, folks. Happy Thursday. Hope everyone is having a great week so far, almost to the weekend. Appreciate folks stopping by, whether you're on the live stream or watching a replay of this later. Today, we're going to be continuing from the last stream, working on decoding RISC-V 64 integer instruction set instructions and looking at how they translate into control signals in the CPU in the MOS computer project, which is what these streams are based around if you've never tuned in before. So we're going to continue with that. I also still have a blog post that we were working on, I think 2 streams ago, that I haven't posted and would really like to get wrapped up and post tomorrow. So we may spend some time on that as well. So without any further ado, I am going to switch over here. And it looks like my camera is already frozen up today, so off to a good start here. Let's see if we can get that corrected. All right, that at least got us back into being live. Looks like I'm going to have to keep it here at this resolution, so we'll just go ahead and switch it over. All right, so it does seem like the stream is coming through okay, and we'll just stay on this and hopefully don't get frozen up anymore for the rest of this. Same time, as I typically say, no one's here to watch my face, so it shouldn't be too big of a deal. We'll have the audio either way. Cool. Well, I think last time we started off by talking a little bit about what we'd work on and maybe sketching some of that out. And I kind of like that pattern, so maybe we'll do that today. So let's go ahead and start off with a to-do list here. Make this large, and we can talk about some of the things that are on the list for today. So I mentioned 1 is RISC-V instruction decoding. 2, finishing up blog posts on lookup tables as excuse me, as distributed RAM. 3 is I wanted to work on some Verilog test benches. Might not get to that today. But I think those are probably the top ones. I can't remember if there was anything else. Oh, the other one is I want to update. We have moscomp.com, which is the home for the MOS Computer Project. Intentionally kind of minimal site here. Long-term goal here, although I'm not sure I've officially put it anywhere, is for the MOS Computer Project itself, or the MOS Computer itself, to be able to host this site. So that is something we hope to do here in the future. But what I wanted to do today was to go ahead and, or maybe not today, but on the list for today, is add links for blog posts and streams to moscomp.com. And that would be pretty easy to get done here. Okay, so I ended up not posting the post that we were working on last time, so I still have it here in draft. I haven't made too much progress on it. Unfortunately, been kind of a busy week, or I guess fortunately. It's always good to be busy. But I did write another blog post kind of at the last minute, the value of live streaming long-term projects. And this is something that I was just kind of thinking about while out on a run. I think it was last Friday. And wanted to kind of get down some of these thoughts. Last Friday, I think it was kind of tedious. We did have some folks stop by, but a lot of these streams are kind of tedious, and I was just kind of thinking to myself about if these are providing value or not, and if they are, what value they are providing. And I kind of concluded that I think they are providing value, which is the reason why I started doing them again, even though they are a little slower, monotonous a lot of the times. Kind of capturing that monotony is part of what I'm trying to accomplish here. And so, it's more stuff for folks to view if they find useful. It's also useful for me for a number of reasons, which I kind of try to caption here as well. One of them, I guess, that's more obvious is it helps hone your public speaking skills. So I'm intentionally not doing a lot of preparation for these streams. So all of this is off the cuff. Things I'm practicing really on a daily basis is trying not to say too much, trying not to use words that don't mean anything, trying not to use flowery language, trying to work on pronunciation, trying to not use flowery language when something more simple and straightforward would work. So kind of all of those are things that I am working on these streams. Two that are actually really big gotchas for me are saying so quite a bit, which I already did in that little monologue there, and also I think saying right. I think someone gave me some feedback on this. I say right too much, so I say something I say right, and I do that a lot of times to kind of prompt feedback. But I think for some folks, it seems it's just kind of like over the top or unnecessary, and so that's another area where I'm trying to improve. So anyway, let's get into it. Let's start building some stuff. Enough of me chatting here. All right, so we said we'd start off with the instruction decoding, and I posted on Twitter and Blue Sky or X or whatever you call it these days, and LinkedIn, that we'd be looking at B and J format instructions. So as a recap, we were looking at the RISC-V 32 base integer instruction set. So the base formats are mentioned here, R, I, S, and U. Let me go ahead and open up the other doc that we spent most of the time on last time, which was ISA. So RISU we mentioned there. And then there are two immediate encoding variants. So RIS and U, and then B is the immediate encoding variant of, let's see, is it S? No, sorry. B is the immediate encoding variant of S, and J is the immediate encoding variant, J is the immediate encoding variant. Sorry, got those switched around there. Cool. So we'll look at how those are used today. Last time, we looked at our R format instructions, and we also looked at our I format instructions. And there's a couple things we kind of took from that. One of the things that I wanted to do here, I put these up in a draft PR, and the formatting is a little weird. Also, the control signals are going to be the same for the same category of instructions. So we could actually minimize that, only include it at the top, and just talk about func3, func7 values. Also, just the formatting as code here is a little weird, but I think it's actually kind of nice for copying. So maybe we'll keep that as is. All right, let me make sure that I am checking the chat. All right, cool. So let's start off, and we have our instruction formats, R format instructions, and then register ALU instructions. So we have some notes about that. Also, all of these are register ALU instructions. So I can move that up here. So there's only one category. I'm trying to think of maybe what a good separator is here. It's a little strange because the add is a little bit larger than the, whoops. I didn't mean to do that, but that works. The add is larger than register ALU, which I don't really love, but that's okay. But what I was going to do was take these control signals and, well, first of all, let's see if we can, take these control signals. They're the same for all of these register ALU ones, and pull them up here. And we know that because they all have the same opcode, right? And we're only considering the opcode when we're doing instruction decoding here. And when we're talking about instruction decoding, just thinking about the signals that we're sending to other components in the CPU from this control unit. So, okay, we have our control signals, and I'm just going to go through here, and we'll get rid of all of these. All right. None of these. And then we'll do the same thing. The control signals change when we get to a different opcode here. When we look at the, let's see, I think the I instructions are up next, yeah. 64-bit register, yeah. So, okay, well, we also do need to include the 64-bit register instructions, which we can see here. So we do have some R format instructions down at the bottom here. That did not highlight very well. Down here. So these are all R format, but you'll notice that they have 0, 1, 1, 0, 1, 0, 1, 1, 1, 0, 1, 1, while these have 0, 1, 1, 0, 0, 1, 1. So different opcode. I don't know if the control signals will be the same or not. Probably something I could intuitively answer here in just a second. Another thing that we talked about last time was the funct3 values in the immediate encoding variant of the register instructions are going to have the same funct3 value. So add immediate is going to have the same as add here. So 0, 0, 0. And maybe SLT would be a more interesting. So we have SLT 0, 1, 0, and then SLTI 0, 1, 0. Cool. All right. Same that we need a section here for 64-bit ALU immediates. And then our load instructions, we do have the control signals here again. We didn't finish up writing them. And we're going to talk about just a second about why some of them are different. Once I move all these out because we have them up top. All right. And let's see, one other thing I wanted to do. Unfortunately, the funct3 and funct7 here get formatted on the same line, which is not ideal. Whoops. There we go. That A to backtick is a weird reach. Really need to. I'm a huge Vim fan, but I don't ever record things, and that is obviously not maximally using Vim here. I kind of want to put these also in a maybe a markdown table. But this works as well. All right, grab 2 more of these and then we're done here. All right, looks good. Register ALU. Other thing I was gonna do was surround these with the line breaks so that they're a little bit separated from one another for now. Okay, load instructions. Cool. So we did R and I, and then we also need to do S, B, U, and J. So maybe I mentioned we're going to talk about the B and J instructions today, but let's start off with S and U actually. And what was the I format? Okay. RISU S format instructions. Okay, so looking at the S format instructions, we can see that we have our opcode as always. We have RS1 and RS2 and funct3, so a further modifier on what the opcode tells us, right? It tells us the operation we're performing. And then 2 immediate fields. So we have this broken into 2 separate ones. Something to note here that I think is a example of a good design decision in RISC-V is the reason why we don't just have, let's say RS2, RS1, and funct3 shifted right, and then these lower 5 bits of the immediate moved up to here, is because when we parse these, we're doing it in hardware, and so everything is happening at the same time, and so it's really useful if we can always get RS1 from the same location in the instructions, because no matter what the format is, we are going to have RS1, and we'll basically just select it or not select it in hardware. And so this makes it really easy when those are always in the same place. I think that might be called out here somewhere. Maybe it's not. Anyway, that's fine. But like I said, we're going to be looking at the bottom 4 here, S, B, U, and J. So let's start with S instructions. And those, we've already done the R type. So unconditional jumps are using the J type, where the J immediate encodes assigned offset in multiples of 2 bytes. Let's find conditional uses B. load and store instructions. Stores are S-type. So we already talked about loads with the immediate last week. So basically, depending on what the funct3 tells us, we are going to load the value, either load byte, load half word, load word, load half word upper, load word upper, I think are what those stand for. And since we're using 64-bit instructions, I think this load word instruction loads a it should be 64-bit, I think. And we'll see here, load and store instructions. Base and offset. Okay, so this is just allowing us to form the address. Base destination. Okay, yeah, looks the same. So we're going to use the ones from the 64-bit base integer instruction set. Just double checking this here. Load half word, load 16-bit value for memory, then sign extends 32 bits for storing in RD. Okay. Okay, so load word still does the same thing. It loads a 32-bit value. It's just whether we sign extended or not. Although a word, that's kind of interesting because if we jump down here, word. Okay, no, it's all the same. Double word. Okay, cool. Never mind. Why is there no LBU? Or perhaps I just missed LBU. Yeah, I did. Okay. Nope, I want that here. Cool. Funct3 is 100. Oh, I must have been off on that. 101. There is no load word upper. Oh, here it is. Okay. Load word upper is 110. So really, when I do the 64-bit ones, I shouldn't really distinguish them because they are an extension and that the format is the same, but the behavior is different. So LBU is 100. And I think LHU is 101. Is that right? Yep, LHU 101. Which I should know because we're just counting up here. Loads an 8-bit value from memory. So these are 16-bit, 32-bit, and 0 extends it. Eight-bit, 16-bit, 32-bit value from memory. All right. Now I mentioned that we would. All right. I mentioned that we would go through the control signals and detail why they are what they are. And so obviously we're not branching when we're loading. Memread instruction or memread signal, HIF instruction specifies a memory address to read. So yes, in this case, we are specifying a memory address to read. So based on the immediate and the register, we'll calculate something in the ALU. And then we'll determine if that value is going to be used to read from memory. Mem to reg is also high if the value written to RD comes from memory. Low if it comes from ALU operation. Right, so we're getting the read address from the ALU, but we're writing back to a register, RD in this case, from the value we read from memory at the address specified by what came out of the ALU. ALU op 00, so in this case it's adding because we have an offset, I believe. And we also mentioned that the ALU op 10 yeah, the ALU op 10 is basically saying we're going to tell you what to do with funct3, I believe. So it's 2 bits, encodes the operation that the ALU should perform, or indicates that the funct field should be used to determine an operation. Okay, so we have to feed the funct fields into the ALU control. So if we wanted to draw kind of what we're getting at here, we have, let's say this is our decoder. So instruction is coming in, and then out of here we have our control signals. Over here we have our ALU, and over here we have our ALU control. So, for example, let's see here. Our ALU control is going to tell the ALU what to do, but that's based off funct3 values coming in here, as well as this control coming in here. So it's basically selecting. So if this is 1, 0, then, and our, let's say funct3 was like 1, 0, 0, then we're saying use this to tell the ALU what to do. And then if this was like 0, 0, for example, we might just say, oh, we need to add. There is no funct3 here, or yeah, in the case of this, we do have a funct3 on all of these, but well, I think that this would be a if we're loading it from memory, has to be sign extended. Let me look at the diagram here. So I think the sign extension is done outside the ALU in this case. Yeah, ALU op. So we're just calculating the address for the read data in the ALU for these load instructions. Just cleaning these up. All right. Where were we? Branch memory, ALU op, mem right. We're not writing anything to memory. We're just reading from memory and storing in the register file. ALU source saying that the memory, the second operand is immediate. Yeah. And then reg write, we're writing back to the register file. So that's high. Okay. Now we can finally get into S format instructions. So these are going to be our store instructions. All right. And it's going to look just like our load instructions for the most part. Except for we have SD, so we have store double word as well. And that makes sense in this case because our register file is going to be X length bytes wide. And so we're 64 bits. So our registers are going to be 64 bits. So we are taking let's say just store double word. We're going to take the value in RS2 and yeah, value in RS2 and store it in memory at the address specified by the base and this offset. Oh, we also have LD. Did we have an LDU? Oh no, LDU wouldn't make sense, right? Because we are on 64 bits. So just like we don't have LWU here. Yeah, so I missed this load double word. It's right in front of me too. Actually, I'm going to grab 0, 1, 1 in the funct 3. Cool. Cool. Store instructions. Let's just take these same ones here. And we're going to say for store, so store byte would be the low 8 bits of the value in RS2 at the address specified. Okay. And also wanted to check if, yeah, the width should, so they should match the loads and stores. So store byte should match load byte, et cetera, because this is specifying the width, right? So the width is 8 bits in both of these. And we don't have any of the upper variants, so I can get rid of those. Lower 16 bits. So the lower 32 bits. Store the 64-bit value. All right, that looks good. Store byte, store half word, store word, store double word. this is true for loads and stores. Oops, opcode. The opcode is 01000011, and that matches 464. Okay, perfect. I think that's why I had the 64-bit variance, because in their own section, because I think that they might have different opcodes for some of the earlier instructions, I mean. Okay. So for a store instruction, okay, cool. We do have these where we can check ourselves. Whoops. But let's not look before. So branch, memory read, memory to register. Nope. ALU op remains 00 because we're getting that address to read from, or to write to, sorry. Mem write, yes. ALU source. Second operand is from register. Second operand is RS2, but wait. Sorry, what is RS1 in the... Did I... Yeah, this should be RS1. For both of these, I believe. Let me double check that here. Yeah, okay, RS1. My bad. Okay, I think I got those all good. Finishing up the opcodes. Where were we? Reg write, no. ALU source. Second is an immediate. So yes in this case. All right, let's check ourselves. ALU source 1. Yep. Mem to reg 0. Okay, so I think it's actually a don't care. Oh, okay. So, the reason why mem to reg is don't care is because if reg write is 0, we're not going to write it back anyway. So we could be either getting... So we could be either writing back to a register a value from the ALU or a value from memory. Like in a load, it would be from memory, or from an R format register instruction, it would be from the ALU. But if read-write is 0, it doesn't really matter which one we select. So let's note that down. Mem to reg is a don't care because whether we write to, because it doesn't matter whether we select the value from the write back value from the ALU or memory if we aren't going to write back at all. And that is indicated by reg write equals 0. Let's say it's inconsequential. Oops. We don't really need that right now. Okay. I need to update all of these. All right, let's keep cruising here. Oh man, already 50 minutes in. I also have a short window today. Ah, Jonathan's here. Hey, Jonathan, I think I missed you while you were on, but thanks for stopping by. Jonathan is a fearless leader at day job and very supportive. Okay. Next up, let's see. So we talked about S instructions. Those don't really, yeah. We talked about S instructions. Let's talk about the B format because that is what we said we were going to talk about today. Okay. So B format instructions, control transfer. Conditional branching instructions. So we have a couple here. Break if equal, break if not equal. branch, sorry, branch if equal, branch if not equal. All branch instructions use the B-type format. The 12-bit B immediate encodes signed offsets in multiples of 2 bytes. The offset is signed extended and added to the address of the branch instruction to give the target address. The conditional branch range is plus or minus 4 kilobytes, I think it would be what that is. Branch instructions compare two registers, break if equal and branch if not equal. I'm going to say branch eventually, I promise. Take the branch registers RS1 and RS2 are equal or unequal respectively. Break if less than and, oh my gosh, branch if less than or branch if less than upper. Take the branch of RS1 is less than RS2 using signed and unsigned. Sorry, this is unsigned, not upper. Using signed and unsigned comparison respectively. You know what? So one of the things that I want to make sure I'm doing all the time is that if something like seems obvious, right? So I mess it up and then I look and it's actually obvious why it would be the case. It's only obvious to me, obviously, after I recognized it. And so I want to make sure that I note those down because someone else who's coming along, maybe it would be more obvious to me if it said it explicitly. So those are things I want to make sure to note down. All right, BGE, take the branch of RS1 is greater than. So we have branch if equal, branch if not equal, branch if less than, branch if greater than or equal to. Software should be optimized such that the sequential code path is the most common path, with less frequently taken code paths placed out of line. Software should also assume that backward branches will be predicted taken and forward branches as not taken, at least the first time they are encountered. Dynamic predictors should quickly learn any predictable branch behavior. So, word to the wise, when there is something like this huge note here, it's always good to read. And we're going to actually talk about this one in just a minute. So these instructions all stay the same for 64-bit. Conditional branches. Okay, we're going to grab the conditional branch instructions here. And here they all are. And we should see that down here that we don't have any branch instruction additions here. Okay, so they all have the same opcode as we would expect. Control signals. Great, we have another one that we can look at here if needed. Okay, so first thing I know is that we're not writing anything back to register. So we once again don't care about this. Branch is 1. Forget how to switch. Let's see. Vim swap panes. That is not correct, it seems. Control. Oh, yeah. Control W, Control R. I want them like this. Okay. Also, I just have to say, my colleague Mike showed me how to properly use the leader hunk for git gutter. So if you do leader HP, you can see what the diff is here. And you can also just stage like this line or just this hunk rather. And same for all of these. So I could see here branch changed, etc. Game changer. Okay, branch high if instruction could result in a branch. Okay, well these are conditional branching instructions. I think yes. Mem read high if instruction specifies a memory address to read. It does not. Once again, we don't care for mem reg. ALU op. We are performing a comparison. So I don't know. I'm going to cheat on this one. It's 0, 1, so I guess that's just how we're saying. Wait, actually. Oops. I think that we're saying... Yeah, we're saying look at funct3, 0, 1. So we've seen this before. Oh my goodness. ALU op 1, 0. Register, register. Okay, no, we haven't seen this before. So it's maybe look at funct3 to determine, yeah, it's still look at funct3, but maybe with branching, perhaps. I don't know, maybe that'll become more apparent to us. And then ALU source is high if the second operand is immediate, low if the second operand is from register. Once again, if we look here, we can see that second operand is from register. So it should be 1. Let's double check that. Sorry, it should be 0. Because the second operand is from register. All right, said the right words. Picked the wrong signal. Funct3 on this one is 0, 0, 0. BEQ, BNE, BLT. If equal, already forgot it. BNE, BLT. BNE, BLT, BGE. Branch if greater than or equal. So this should be, let's see if we can get this right. 1, 2, 3. Nope. 0, 1. And this was 1, 1, 0, I think. Nope, 101. All right, and then to round out, we have BLTU, BGEU. So we just take these two. BLTU, BGEU. And those are 110, 111. All right. All right, I'm going to get these completed and then probably call it a day. Where are we at? Control transfer. Unconditional jumps. Conditional branches. All branches used to be type 12-bit, be immediate, encodes signed offsets in multiples of 2 bytes. The offset is sign extended and added to the address of the branch instruction to give the target address. Offset address of the branch instruction. So we add this to the program counter. Okay, that makes sense. All right, let me note that down up here. $12-bit, 12-bit immediate. Encode signed offsets and multiples of 2. The branch destination location. Target address. That works. Conditional branch range is okay. So this makes sense because we have so why don't we have the first bit, right? Because it's multiples of 2 bytes. And it's byte addressable. So we have 12 to the second, right? Sorry. Was not thinking. 2 to the 12th. 4096. So 1 KIB. 1 kilobyte is how many bytes, right? 1024. What is 1024 times 4? 4096. So that's why we have plus or minus 4 kilobytes. All right. You know what? I think that's a decent place to leave it for today. Thanks to everyone for tuning in here. Let's see if I can actually get my camera rework in here. Best I can do is centering it, kind of. We'll give it a shot anyway. All right, I'll pop over here. Okay, thanks everyone for tuning in today. I know it's a bit monotonous. I'm going to spend some time after this continuing to work on the blog post. Hopefully, can get it done for tomorrow. Also, thinking about doing some more of the RISC-V tips that I used to post in various places. I think they were really good for just keeping people engaged and getting stuff out there more frequently. So I think I'm going to look at taking some of the things we talked about today, maybe just talking about that little calculation we just did. Why are conditional branches in RISC-V plus or minus 4 kilobytes, right? It's because we have 12 bits and we really have 11 bits, but we don't care about the first bit because we only do multiples of 2. So I might post something about that. But anyway, I hope everyone has a good Friday tomorrow and has a nice weekend. And thanks for stopping by as always. Really appreciate it.